Today what we are going to do is we have two errors in the gyro compass. One is the latitude error or the damping error or settling error. Second is the steaming error or CLSE. The video which I had sent you is the CLSE steaming error fundamental. So we will do the second error also now, the settling error, damping error or latitude error. So we will cover that error and I will give a recap of the steaming error formula also. So once we are comfortable with these two errors and their formula, then we will go into numericals. Numerical question which are based on gyro errors. So ready to go ahead beta? Ready? शुरू करें?
Yes, sir.
Okay, all right. So let me put up the presentation. Let's go. In this presentation, we are going to discuss and learn about the errors of the gyro compass. We have seen in the concept and working of the gyro compass that it is based on a free gyroscope which is gravity controlled, and its circular motion turns into a elliptical motion, and then it is damped, in which the elliptical motion converts into an inward spiral, and eventually it settles down and gives us a fixed directional reference. But the settling position of the gyro may not be exactly in the meridian, or in other words, the gyro may not show us the true north. This is because of some of the errors which may come in the working of the gyro compass. So we are going to understand what these errors are, what are the causes of these errors, and how these errors can be calculated and eventually rectified or compensated. So discussing on the same lines, the headings or the directions given by the gyro compass have some inherent errors in them. The most significant of these errors are: number one, the settling error, also known as damping error and also known as latitude error. The first error which we are going to discuss is represented by these three names: the settling error or the damping error or the latitude error. The second most significant error of the gyro compass is the course, latitude and speed error. In
Good evening, sir.
Hello, beta. Good evening.
Good evening, sir.
Good evening. So, how are we today?
Good, sir. Good. How are you, sir?
All well, beta. All well. Okay. So, beta, did you go through the steaming error CLSE video?
Yes.
Okay. So, have you understood the formula?
Yes, sir.
Okay. All right. Great, beta. Great. So, today what we are going to do is we have two errors in the gyro compass. One is the latitude error or the damping error or settling error. Second is the steaming error or CLSE. The video which I had sent you is the CLSE steaming error fundamental. So we will do the second error also now, the settling error, damping error or latitude error. So we will cover that error and I will give a recap of the steaming error formula also. So once we are comfortable with these two errors and their formula, then we will go into numericals. Numerical question which are based on gyro errors. So ready to go ahead beta? Ready? शुरू करें?
Yes, sir.
Okay, all right. So let me put up the presentation. Let's go. In this presentation, we are going to discuss and learn about the errors of the gyro compass. We have seen in the concept and working of the gyro compass that it is based on a free gyroscope which is gravity controlled and its circular motion turns into a elliptical motion and then it is damped in which the elliptical motion converts into an inward spiral and eventually it settles down and gives us a fixed directional reference. But the settling position of the gyro may not be exactly in the meridian, or in other words, the gyro may not show us the true north. This is because of some of the errors which may come in the working of the gyro compass. So we are going to understand what these errors are, what are the causes of these errors, and how these errors can be calculated and eventually rectified or compensated. So discussing on the same lines, the headings or the directions given by the gyro compass have some inherent errors in them. The most significant of these errors are: number one, the settling error, also known as damping error and also known as latitude error. The first error which we are going to discuss is represented by these three names: the settling error or the damping error or the latitude error. The second most significant error of the gyro compass is the course, latitude and speed error. in short known as CLSE, C for the course, L for the latitude, S for the speed, E for error, and it is also known as steaming error. Now the second error which we have gets its name as steaming error because this error is present in the compass only when the ship is moving or steaming. If the ship is not steaming and is stopped, in that case the second error is absent. It is not there. That's why the name given to it as steaming error. We will now understand the causes of these errors. What are the factors which bring these error in the gyro readings? And we will see how can these errors be calculated and eventually rectified or compensated. So starting off with our first error, which is known as settling error, damping error, or latitude error. Now the diagram which we see is the same spiral motion of the damped gyro which we have seen and understood under the damping of the gyro compass. This is for an observer in the Northern Hemisphere. Now we have observed in this spiral motion that the settling position, where the settling position is, at the settling position, all the four forces which are at play here are balancing out each other. That is, the drifting force is equal and opposite to control precession, and the tilting force is equal and opposite to damping precession. Also, we observe that the settling position is above the horizon. You can see this is the horizon represented in the diagram, and we see clearly that the settling position is above the horizon. And also, the settling position is east of the meridian. You can see this vertical line, which is shown by the laser pointer, is the meridian, and we can see that our settling position is east of the meridian. Let us now try to understand why the spin axis settles east of the meridian, why not west of the meridian, and why the spin axis settles above the horizon, why not below the horizon. So we will understand the balance of these four forces, and that will make us clear why the settling position is attained at this particular location only. Now, if you have a careful look at the four forces which are present in this spiral motion, these are the red color vector showing the tilting, blue color vector showing the drifting, green color vector showing the control precession, and the yellow color vector showing the damping precession. Now, out of these four forces, if you have a look at tilting, tilting is dependent upon the azimuth of the spin axis. And we can see at different locations in the spiral motion, as the azimuth of the spin axis changes, the tilting force or the red color vector also changes in direction as well as magnitude. The forces control precession and damping precession are both proportional to tilt of the spin axis. And we can see in the diagram that as the tilt of the spin axis changes at different locations in the spiral, the control precession and damping precession also change their directions as well as magnitudes. At the horizon where the tilt is 0, PC and PD, both these forces are 0. And as the tilt goes up or down, PC and PD are also generated. Now coming to the fourth force which is present, that is drifting. If you look carefully, drifting remains constant throughout at all the positions of the spiral motion. Because drifting is only dependent upon the latitude of the observer, and for a stationary observer, the drifting is going to be constant in direction as well as magnitude. And you can see in the spiral also at all the locations, the drifting vector, which is the blue color vector, has the same direction, easterly direction, and has the exact same magnitude. So irrespective of wherever our settling position is, this drifting has to have the same magnitude as well as the same direction there also. So we will have this drifting force in the easterly direction and with this much of magnitude. Now we know that at the settling position, this drifting has to be counteracted or cancelled by control precession. Now to cancel out easterly drifting, we have to generate a westerly control precession. And from the control precession formula, we are aware that a westerly control precession is generated when the tilt is up. Whenever the tilt is up, a westerly control precession is generated. You can have a look at Bravo, Charlie, Delta. Wherever the tilt is up, we have a westerly control precession generated. This is the reason that the settling position has to be with a up tilt, or it has to be above the horizon. When the settling position is above the horizon, we will have a up tilt. Up tilt generates a westerly control precession, which cancels out the easterly drifting. Thus, cancelling out these two forces, they balance out each other. You can also have a look at point Bravo. At point Bravo also we had the drifting and control precession exactly equal and opposite to each other. You can have a look at point Delta also. At Delta we had the drifting and control precession equal and opposite to each other. And this settling position is at the same level as we had at Bravo and Delta. Now whenever we have a up tilt, we know that up tilt will be generated to generate the desired control precession. But whenever there is a up tilt, the damping precession is also generated, and the direction of the damping precession is always opposite to the direction of tilt. If we have a up tilt, the damping precession will be downwards. So we will have a downwards damping precession generated because of this up tilt. And now to cancel out this downward damping precession, we will need to have a upward tilting. This downward damping precession can only be counteracted or cancelled with a upward tilting. So we need to have upward tilting equal and opposite to the downward damping precession which is generated because of up tilt. Now we are aware that tilting is upwards whenever we are east of the meridian. Whenever the spin axis is east of the meridian, the tilting is upwards. You can have a look at Bravo, at Golf, at Alpha. All these points are east of the meridian and the tilting is upwards. So to have a upward tilting, we need to have a easterly azimuth of the spin axis, and this is exactly the reason why our spin axis settles east of the meridian. So when it goes east of the meridian, a upward tilting is generated which is equal and opposite to downward damping precession, thus cancelling out each other. This is the reason why the spin axis is above the horizon and east of the meridian in the Northern Hemisphere. Now when we go to the Southern Hemisphere, in the Southern Hemisphere, the drifting direction is reversed. In the Southern Hemisphere, the drifting vector points westwards. So if it points westwards, the control precession which needs to be generated to cancel this one is the easterly control precession. Easterly control precession is generated when we have a down tilt. So in the Southern Hemisphere, the settling position is below the horizon with a down tilt. With a down tilt, a upward damping precession will also be generated, which is countered by a downward tilting motion, and a downward tilting motion is obtained west of the meridian. So in the Southern Hemisphere, the settling position is below the horizon and west of the meridian. In the Northern Hemisphere, as we see in the diagram, the settling position is above the horizon and east of the meridian. Now this difference which we see between the meridian and the settling position which is represented by this maroon color arrow, this is the damping error or the settling error or the latitude error. Any doubts up to here, beta? Very
सर ये
good.
सदर्न हेमिस्फीयर का वो नहीं कर पाए इमेजिन.
Okay. Just remember this much, that in Southern Hemisphere this error is westerly. That's enough, beta.
ओके सर, ठीक है.
Okay. So as just now discussed, we can see the adjoining spiral made in the northerly latitudes, and the settling position is above the horizon and east of the meridian. Now this error can be easily calculated for a given latitude and can be applied manually if required. However, in modern gyro compasses, the error is automatically calculated from the latitude, which is fed in by the GPS and is applied automatically. In the old design of gyro compasses, we had these two inputs going into the gyro compass. One input was for the latitude and another input was for the speed. The latitude input, there were two big knobs fitted somewhere in the chart room, and the duty officer was required to set those knobs to the actual latitude of the ship and the actual speed which the ship was doing. Once the knob is put into the particular latitude, there is a software inside the gyro which calculates the damping error, and then it applies that damping error and counteracts it, and the figures or the readings which are shown to the navigator are the corrected figures. But in modern compasses, this is not required at all, because in modern compasses, the gyro is fed in with the latitude of the ship directly from the GPS. So you have a GPS feed going into the gyro gets the latitude of the ship. The software, once the latitude is obtained, calculates the damping error and counteracts it, applies it, and the readings which we obtain from the digital display or from the analog display of the gyro are the readings which are already corrected for this error. Moving ahead now. Now, one important thing to understand and keep in mind is that this particular error, that is the settling error or damping error or latitude error, occurs only in the gyro compasses which are damped in tilt. We had seen that there is two types of damping which is possible. Either the compass can be damped in tilt or the compass can be damped in azimuth. Now, this error is not present in compasses which are damped in azimuth. This is only present in the gyro compasses which are damped in tilt. Keep this in mind. This fact is used in the numerical sometimes. When they provide you a numerical, they mention to you whether the compass is damped in tilt or damped in azimuth. And accordingly, we have to see whether the settling error will be present in that compass, damping error will be present in that compass or not. Now, let us see the derivation of the formula, how the damping error formula is derived, and it helps us to calculate the exact value of the damping error. Now, we just saw that at the setting position, drifting is equal and opposite to control precession. So the magnitudes are equal and the directions are opposite. And also tilting is equal and opposite to damping precession. You can see the blue arrow representing the drifting is equal and opposite to the green arrow, which is the control precession. The red arrow, which represents the tilting, is equal and opposite to the yellow arrow, which is the damping precession. Now we are aware of the drifting and tilting formula. The formula for drifting is 15 degrees sine of latitude. Since it is equal and opposite to PC, we get this relationship or equation number 1. Drifting is equal to control precession, or 15 degrees sine of latitude is equal to PC. Exactly in the same way, since tilting is equal and opposite to damping precession, tilting is given by 15 degrees sine of azimuth cos of latitude. It is equal to the damping precession, which we represent as PD. Now we have these two equations in front of us. What we are going to do is we will divide the equation number 2 by equation number 1. And as we do it, we get the relationship 15 degrees sine of azimuth cos of latitude divided by 15 degrees sine of latitude is equal to PD upon PC. 15 gets cancelled in the numerator and the denominator, and we are left with the formula sine of azimuth. This value is kept on the left hand side, is equal to PD upon PC, PD upon PC, and you see the cos latitude upon sine latitude is taken onto the right hand side of the equation, and when it goes on the right hand side it becomes sine lat upon cos lat, which converts to tangent of latitude. So we get the relationship sine of azimuth is equal to PD upon PC into the tangent of latitude. Clear up to here, beta? Very good. Moving ahead now. So this is the relationship which we have got. Now the ratio of PD to PC. PD is damping precession and PC is control precession, is also known as the damping ratio. And this ratio is constant, represented by alphabet K for any particular compass. So for a compass which is fitted on a ship, this ratio, the damping ratio PD upon PC, is fixed and constant. The Sperry make compasses are having this ratio exactly matching to 1:40. So how is this 1:40? Let me take you back a little bit. When we discussed about the concept of the gyro compass, I told you there are two weights which are fitted on a gyro compass. One weight, the bigger one, is used to make the compass top heavy. Now that weight, if you remember, is 680 grams. The most effective weight which can be used to control and dampen the gyro is the 680 grams weight, which is used to make it top heavy. Now there was another weight which we used to dampen the compass, to make it north seeking, to make the motion an inward spiral, and that weight was 17 grams. Now the top heavy weight, 680 grams, is what generates the control precession, and the small weight, which is 17 grams, is what generates the damping precession. So 17 gram is to 680 grams is exactly the ratio of 1:40. 17 fours are 68. So 17 grams to 680 grams is this ratio of 1:40. The damping precession, which is generated by the smaller weight, 17 grams weight, proportional to control precession, which is generated by the bigger weight, which is 680 grams weight, gives you a damping ratio of 1:40. Now, when we use this 1:40 ratio, the formula converts to sine of azimuth is equal to K tan latitude. PD upon PC is replaced by K, where K is equal to 1/40 in Sperry compass. Now, in other makers also, you could have a Tokamak compass or a Anschutz compass. In other makers also, the ratio is kept very close to 1/40. It could be exactly 1/40, but it could vary a little bit. In some case, it could be 1/39, or in other case, it could be 1/41 also. But the ratio does not go too much off from this 1:40 figures. Now, as far as our questions are concerned, if the damping ratio of a compass is provided to us in the question, we will use that value which is provided. They may either provide this information to us straight away, telling that the damping ratio of the compass was 1:40, or they may give us some information with which it can be easily calculated. So in both these cases, when it is directly provided or some information is given with which it can be calculated, we use the given value. But if in some question the damping ratio is not provided to us, we use this ratio of 1:40. So if you need this for your calculation and it is not given to you in the question, it is to be considered and taken as 1/40 ratio. So when you use this damping ratio and you use this formula, the azimuth what you obtain here is nothing but the settling error. As you can see in the diagram, the azimuth here is what the difference between the meridian and the spin axis is. The azimuth basically tells you what is the direction in which the spin axis points. So whatever azimuth you obtain from this formula, this azimuth is your damping error. Clear up to here, beta? Any doubts, beta?
Yes, sir.
Go ahead, beta. Joshua, any doubts, beta?
No, sir.
Okay, all right. Great. Let's move ahead. So let's summarize the formula now. Sine of damping error is equal to K into tangent of latitude, where K is equal to 1/40 if not given in the question. Now this formula is going to give you the magnitude of the damping error. It will give you the magnitude of the damping error. Now we also need to find out whether the damping error is easterly or the damping error is westerly. Now, as we just now discussed in the explanation in the previous slides, that the compass always settles east of the meridian when you are in a northerly latitude. So that is the reason the error is easterly on northerly latitudes. If you are in the Northern Hemisphere, the damping error will be east. Now, an easterly error is also known as low error. In fact, in case of the gyro, the low and high format is more frequently used to indicate the error of the compass. East and west is more frequently used in case of the magnetic compass. But both these terms are interchangeable. You can denote the error as east or you can denote the error as low. Now, this can be easily memorized by remembering the idiom error east, compass least. So it tells us whenever the error is east, the compass will be least or the gyro error will be low. And whenever the ship is in southerly latitudes, you are in the southern hemisphere, the error will be west because the spin axis in that case settles west of the meridian. So westerly error is also known as high error. So we are aware of the idiom error west, compass west. So you can represent it as westerly error or you can represent it as high error. Both are interchangeable. So error is low or east in the northerly latitude. Error is high or west in the southerly latitudes. So this summarizes the damping error formula. So very, very important formula. And this is what the questions on gyro compass, numerical questions on gyro compass are based upon. The questions which we get in the exams are based upon the gyro errors. And this is the first important formula for the damping error. There are only two formulas here for gyro numerical. One is this one, which you are seeing on the screen right now. The second one, which we are going to discuss, is the formula for CLSE or steaming error. So this completes the explanation of damping error. Any doubts in damping error, beta? Okay, beta. Great. Very good. So let me now give you a recap of the steaming error formula also. You must have seen that in the video, but let's give a recap. Let me now take you to the final formula which can be used in any of the quadrants. The formula which we have is tangent of CLSE is equal to V cos course divided by 900 cos lat plus minus V sin course. CLSE is the course latitude speed error or the steaming error. V is the speed of the ship. Course is the quadrantal course on which the ship is moving. 900 cos latitude, it is the latitude where the ship is, plus minus V sin course. V again is the speed of the ship and course is the quadrantal course on which the ship is moving. Now in the denominator we have a plus and minus sign here. When do we use a plus and when do we use a minus? The positive sign or plus sign is used for easterly courses and the negative sign is used whenever the vessel is moving on westerly courses. So if the ship is moving on a northeasterly course or a southeasterly course, we will be using a plus here in the denominator. And if the vessel is moving on a northwesterly course or a southwesterly course having a westerly component, we will be using a negative sign here. You can easily understand the concept behind it. When the ship is moving in the easterly direction, it is adding up to the easterly motion of the ship. The easterly motion of the earth. And whenever the vessel is moving in a westerly direction, it is reducing the easterly motion of the earth. Now, once we put all these values here in the formula, we are going to get the magnitude of the CLSE or the steaming error. Now, how do we determine whether this error is east or west, whether this error is low or high? Now, for that, error is high or west on northerly courses and the error is low or east on southerly courses. If the vessel's course is having a northerly component, that means vessel is moving on a northeasterly course or a northwesterly course, the error is going to be west or high. West and high are interchangeable. You can easily confirm it from the idiom which we use for applying the compass error. error west, compass west. So a westerly error is also mentioned as high error. Whenever the vessel is moving on a southerly component course, that is a southeasterly course or a southwesterly course, the error is going to be east or low. Again, east and low are interchangeable. We can confirm it from the idiom error east, compass least. So in case of a southerly component course, the error is going to be easterly or low. Now be careful when you are applying this formula. The easterly or westerly component of the course decides whether we will be having a plus or minus sign here in the denominator, whereas the north and south component of the course decides the sign of the error, whether the error is going to be high or low. Clear, beta? Any doubts?
Sir, this V is the speed.
Yeah, V is the speed of the ship, beta.
Okay.
Okay, all right. So with these two, now we are ready to go into the numerical questions. So let me show you the numericals one by one. We'll start with simple ones and then slowly proceed to the more complicated ones. So let me put up the presentation for numericals. Now, if you want, you can take a screenshot of this particular slide. This slide has both the formulas, the damping error, latitude error, settling error, first one, and the CLSE or steaming error. Both the formulas are given here. So just take a screenshot and keep it in front of you for reference. We will be using these formula when we are solving the numerical questions. Great. So let's move on, beta. I'm moving on to the first numerical now. We have the first question on the screen. A gyro damped in tilt has a damping error of 2.8 degrees in latitude 58 degrees south. Find the damping error in latitude 30 degrees north. Now we are aware the damping error formula is given by sine of damping error is equal to K tan latitude. So in this question you see they have given us the damping error as 2.8 degrees and they have given the latitude also 58 degrees south. So let's put these values in the formula and it gives us sine of 2.8 degrees is equal to K into tangent of 58 degrees. Now this relationship gives us the value of K as sine of 2.8 degrees divided by tangent of 58 degrees. So you see in this particular question, they have given us sufficient information that we can obtain the value of K, the damping ratio for this particular compass. Now once this damping ratio is obtained, then we can use this damping ratio to get the answer. Now the question says we have to find the damping error in latitude 30 degrees north. So again using the damping error formula, calculating the damping error in latitude 30 degrees north now. The formula tells us sine of the damping error is equal to K tan latitude. In this case latitude will be 30 degrees Using the value of k as sine of 2.8 degrees divided by tangent of 58 degrees, you put it in the calculator, you will get the damping error in latitude 30 degree north as 1.01 degrees east or low. As you put the value of k in the calculator, it will give you the magnitude as 1.01 degrees, and we are aware that the damping error is always east or low in northerly latitudes. The latitude which is given to us is 30 degrees north, hence the gyro error is also east or low. East and low are interchangeable. You can denote it by either writing as easterly error, or you can write it as the gyro is 1.01 degrees low. So this completes our question number 1. Clear beta? Simple.
So the question that damping error 2.8 degree 58 degrees south, then it will be 2.8 high or west, right?
Yeah, that's correct beta. It will be 2.8 degrees west or high.
Okay.
Okay. So let's move on to the next one. Moving on to the next question. Question number 2 says, if the damping error is 1 degree east in latitude 35 degrees north, calculate the combined damping and course and speed error when steering 346 degrees true at 16 knots in latitude 52 degrees south. So beta, is the question clear? Any doubts in the question? Okay, all right. Let's move ahead. Now you see the question gives us the value of damping error at a particular latitude. This is very much similar to question number 1. The damping error was given to us, the latitude was given to us, and using these two, we were able to find out the value of k for this particular compass. So that will be the first step in this question also. We need to get the combined damping and course and speed error. So we need to get the damping error as well as the course and speed error or steaming error or CLSE when the vessel is steering 346 true. So the course is given to us at 16 knots. The speed is also given to us, and latitude 52 degrees south. The latitude is also given to us. So it will be a simple application of the steaming error formula. Let's now see the solution. First of all, applying the damping error formula with the information provided. Sine of damping error is equal to k tangent latitude. Using it for latitude of 35 degrees north, which is given to us in the question. The damping error is given as 1 degrees east. This gives us sine of 1 degree is equal to k into tangent of 35, and it gives us the value of k as sine of 1 degree divided by tangent of 35 degrees. So we have obtained the value of k for this particular compass. Now using this value of k for 52 degrees south latitude. Now this is the latitude where we need to find our answer, the combined damping error and the CLSE. So first of all, we will get the damping error for this latitude 52 degrees south. So using the formula once again, sine of damping error is equal to k tan 52. Value of k is known to us now. So multiplying it with tan of 52 and taking a sine inverse will give us the damping error as 1.828 degrees. Now calculating these values, you can go up to say about 3 places after the decimal. Practically on board we use the information only up to accuracy of 1 place after the decimal. So that is the maximum resolution which may be required practically. But in these numerical questions, just to get a exact or accurate answer, you can go up to 3 places after the decimal. So we get the magnitude of the damping error as 1.828 degrees. And the sign of this damping error, you see the latitude is given to us as 52 degrees south. Now in southerly latitudes, the direction of the damping error or the sign of the damping error is west or high. So we have obtained the damping error for latitude 52 degrees south. Now in the second part, we obtain the CLSE, course latitude speed error or steaming error. The formula for CLSE is tangent of CLSE is equal to V cos course divided by 900 cos latitude plus minus V sine course. Plus sign is used whenever we are on a easterly course, a course having a easterly component, either in the northeasterly quadrant or the southeasterly quadrant, and a negative sign is used when we have a westerly component in the course. That means the quadrantal course is either in the northwest quadrant or the southwest quadrant. Now in this case, the course is given as 346 degrees true, which is a northwesterly course. So we have a westerly component telling us that we will have a negative sign here in the denominator in the CLSE formula. Now putting all the given values, we get tangent of CLSE is equal to V is 16 knots, the speed is 16 knots, cos of course, so course is 346 degrees. We always use quadrantal notation course in the formula. So converting into quadrantal notation, we get it as north 14 degrees west. So the value of V cos course becomes 16 cos 14 whole divided by 900 cos latitude, the latitude is 52 degrees, minus V sine course, V is 16 knots and the course is 14 degrees, so 16 sine 14. Now putting this in the calculator, you get the CLSE as 1.616 degrees. Now to obtain the direction or the name of the CLSE or the steaming error, we are aware that the steaming error on northerly courses is always west. Whenever there is a northerly component in the course, that means the course is either northeast or northwest quadrant course. In that case, the error will always be west. If the course has a southerly component, that means the vessel is moving on a southeasterly or southwesterly quadrant. Now in that case, the error would be east. So in this case, a northerly component of the course tells us the error to be west or high. Now we have both the errors known to us. Damping error is 1.828 degrees west. CLSE is 1.616 degrees west. Combining both these errors together, since they are both of the same names, we add them together and get the complete or total gyro error as 1.828 degrees plus 1.616 degrees. The answer comes to 3.444 degrees and the direction remains west or high. Any doubts in this beta? Okay beta, great. Moving ahead.
Excuse me, sir.
Moving. Go ahead, beta.
This question, we have to show the diagram for a steaming error also. Diagram, rough diagram. Direction.
In this question, beta,
Steaming error.
number 2 question.
Yes, sir.
Not required, beta. No need of making any diagrams. Diagram for CLSE is required only if they tell you to derive the formula. They ask you what is the course latitude speed error, derive the formula for CLSE, then you need to make the diagram. Otherwise, for these questions, no diagram is required. Okay.
सर ये जो साइन बताया आपने for the vessel steaming north we take it west LSE and for vessel steaming south we take it east. What about this thing 090 and 7?
Beta, you are not coming clear. Can you speak little slowly?
सर ये अपना the sign for CLSE
Right.
सर वो north के लिए we took it east and for south for north we took it west.
Right.
हाँ सर ये 270 और इसके लिए क्या लेंगे और
किसके लिए बेटा? East or west? Okay.
270 4090.
Okay, beta. Okay. Now, if you are moving east or west, beta, you see the formula has V cos course. Moving easterly, it will be cos of 90. Cos 90 becomes 0. So, on easterly courses, the CLSE or steaming error will be 0. So, you will not need to take a sign.
Okay, sir.
And same for 270, beta. Cos of 270 is also 0. So, the CLSE or steaming error is nil on easterly and westerly courses.
Okay, sir. Thank you, sir.
Okay, all right. Good. So, this was question number 2. Now, moving on to number 3, beta. Moving on to the next question. A gyro dammed in azimuth had the corrector for speed and latitude set at 0. The ship is doing 18 knots in latitude 32 degrees south on a course of 321 degrees gyro. Find the gyro transit bearing of a set of lights if their charted transit bearing is 177 degrees true. Now, at the first instance, this question looks little difficult to understand. They are talking of a speed and latitude corrector. We don't have any such corrector in the modern generation gyros which we use nowadays on board. Now, in this question, they are talking about old generation gyros in the pre-GPS era when there was no GPS available on board. So that time we used to have these old generation gyros which had a corrector for speed and latitude. Basically, there were two big knobs somewhere in the chart room, one of them for putting in or feeding in the speed and the other one for feeding in the latitude. The purpose of these knobs, the speed and latitude knobs, was to give a input of what is the current speed of the ship and what is the latitude of the ship to the gyro compass. You see, these are the two parameters which are required to calculate the gyro errors. Whether it is the damping error or the steaming error CLSE, in both the cases, we require what is the speed of the ship and what is the latitude of the ship. So these were fed manually. Since there was no GPS, both these pieces of information were fed manually through these knobs. Now, sometimes it used to happen that the vessel came out from a port and the duty officer forgot to update these speed and latitude in the knobs. The knobs were kept at 0. Let us say the speed was kept at 0. The ship was at the equator. Latitude knob was also kept at 0. Now the vessel has started moving. It has changed its latitude. It has gained some speed. But the duty officer forgot to adjust these knobs to update the speed and latitude. So what will happen in that scenario? So what happens in that scenario is the gyro is not aware that the speed has been picked up, the latitude has been changed. So the gyro does not apply any correction to the readings. If you adjust these knobs to the present latitude, to the present speed, what the gyro does is the software calculates both these errors, that is the damping error and the steaming error, and applies them to the gyro readings, and the readings which you get are the corrected readings. Now, if these knobs are not properly set, the gyro will not be able to apply these two errors in the readings, and whatever readings you obtain from the gyro will have these errors included in them. So this is the meaning of these speed and latitude correctors. So let's try to now see the solution of this question. The first thing which is given to us is that the gyro is damped in azimuth. Now we know for the compasses which are damped in azimuth, there is no damping error. So that's why there is no damping error in this gyro compass. Damping error is only present in compasses which are damped in tilt. Also, since the latitude and speed corrector is set at 0, this means that the steaming error, the CLSE, is not being corrected, and the gyro readings will have this error included in them. So whatever readings we are obtaining from the gyro compass will have the steaming error in them, and to get the actual readings we will have to apply or take out this steaming error from those readings. Now to find the gyro transit bearing of the set of lights, we need to calculate this error. Once we are aware of what this error is, we will be able to apply it to the gyro readings and then get the gyro transit bearing of the set of lights. So we go into the formula for the steaming error, that is tangent of CLSE is equal to V cos course divided by 900 cos lat minus V sine course. Now we have a minus sign here because the course which we have is 321 degrees, which is a northwesterly course. So whenever the course has a westerly component, we have a negative in the denominator of the steaming error formula. Putting the values here, the speed of the ship is given as 18 knots. The course is 321, which is north 39 degrees west. So we have the course as 39 here. We use the course in the quadrantal notation. Then in the denominator, you have 900 cos of latitude, which is 32 degrees, minus V, which is 18 knots, sine of course, which is 39 degrees. Now when we put these values in the calculator, we get the CLSE or the steaming error as 1.066 west or high. Now the magnitude is obtained from the formula, and the sign of the error, that is west or high, is obtained from the fact that the course which we have, which is 321 degrees, has a northerly component. Whenever the course has a northerly component, this is a northwesterly course. So whenever the course has a northerly component, the steaming error is always west or high. Now we know that the charted transit bearing or the true bearing of the transit bearing of the lights is 177 degrees true. The gyro error is 1.066 high. So the gyro transit bearing will be 1.066 higher than the actual or charted transit bearing. So to obtain the gyro transit bearing, we add 1.066 to 177. And we get our answer as 178.066, which will be the gyro transit bearing of these lights. Have a good look, beta. Let me know if any doubts are coming in. Clear, beta? Understood? Okay, all right. Let's move ahead then. Moving on to the next question. The spinning axis of a gyro compass, damped in tilt, uncorrected for damping and steaming errors, is pointing due north in latitude 61 degrees south, while making good a course of 165 degrees true at a speed of 20.6 knots. What will be the direction of the spin axis when making good a course of 345 degrees true at a speed of 13.3 knots in latitude of 61 degrees north? Now have a good look at the question, beta. Let me know if any doubts are there in the question itself. Okay, let's go into the solution. Now, at the first instance, the question looks a little surprising. Why surprising is because it is mentioned in the question that the gyro compass is uncorrected for damping and steaming errors. That means whatever heading or readings the gyro is giving us, the damping error and steaming error will be present there. But even a uncorrected compass is pointing due north in latitude 61 degrees south. Now, since the compass has these errors, the damping error and the steaming error, it should not have pointed due north. But even after having these errors, the compass is still pointing due north. So what could be the reason for it? Let's see. The gyro compass is uncorrected for damping error and CLSE or steaming error, but still points due north. Now this is only possible if the damping error and the steaming error are exactly equal and opposite, thus cancelling each other. Since the compass is uncorrected, damping error will be present, the steaming error will also be present, and the only way you could have a zero gyro error is if both these errors cancel out each other. That means they are equal and opposite. So let us first calculate the CLSE. We have all the information available to us for calculating CLSE. The formula tangent CLSE is equal to V cos cos divided by 900 cos lat plus V sin cos. We have a positive sign here because the cos is 165 degrees true, which is a easterly component course. It's a southeasterly course. Putting the values here, we get the formula 20.6 cos of 15 degrees, 900 cos of 61 plus 20.6 sine of 15 degrees. The course is south 15 degrees east, which is 165 degrees true. The speed is 20.6 knots given to us, and the latitude is 61 degrees south. So when we put these in the calculator, we get the steaming error as 2.580 degrees. The name of the steaming error will be east or low. Now why is it east or low? That's because the course which we are having, 165 degrees true, is a southeasterly course. It has a southerly component. Whenever the course has a southerly component, the steaming error is always east or low. So we have the steaming error available to us now. Now, since we know that the damping error and CLSE are exactly equal and opposite in this case, the damping error will be exactly opposite. That will be 2.580 west or high. So this tells us that the damping error for this particular compass at this particular latitude has to be 2.580 degrees west. And this is the reason why the gyro is pointing due north, because both of these are equal and opposite, cancelling each other.
Sir,
Go ahead, beta.
instead of calculating CLSE, we can use the ratio 1:40 and calculate damping error instead.
ओके बेटा, अब बेटा अगर हम वो करेंगे ना, देखो यहाँ पे इन्होंने हमें जो k की वैल्यू है वो प्रोवाइड नहीं की है. So we will have to assume that k is equal to 1/40, right? That's number one. And number two, even if you do that, the CLSE and damping error may not match with each other. So that will be extra information in the question. So he does not want you to calculate the damping error. He wants you to calculate the CLSE and equate it to damping error.
Okay, sir.
Okay. So since k is not given, we will first calculate the CLSE. For CLSE, everything is given to us. So that gives us a hint that we calculate CLSE first and then get the damping error. Okay, great. Let's move ahead. Now, we want to calculate the gyro error on a course of 3452 at a speed of 13.3 knots in latitude 61 degrees north. In the first case, the latitude was 61 degrees south. In the new situation, the latitude is 61 degrees north. If we go to the same northerly latitude, the magnitude of the damping error will remain same, but the sign will be reversed. You see, putting the same thing in the formula k tan lat, whether it is 61 degrees south or it is 61 degrees north, the magnitude of the damping error remains same. Only thing is the naming of the error now changes from west to east, because in northerly latitudes the damping error is always east or low. Hence, the damping error in latitude 61 degrees north will be 2.580 east or low. So we have obtained the damping error in the 61 degree north latitude. The damping error in 61 degree north is 2.580 east or low. Let's proceed ahead now. Now moving further, let us calculate the CLSE for the new latitude and course. We have the damping error available now, which is 2.580 east or low as calculated in the last slide. So moving on to CLSE or the steaming error. Tangent of steaming error or CLSE is equal to V cos course divided by 900 cos lat minus V sin course. Why negative sign here? Because the course which we have 345 has a westerly component. It's a northwest quadrant course. Whenever the course has a westerly component, we have a negative sign in the denominator. Putting the values, the speed is 13.3 knots. Cos of course is north 15 degrees west. So we use the value of 15 here. 900 cos of latitude is 61 minus V cos course, V sin course, V is 13.3, sin of course which is 50. Putting these values in the calculator gives us the steaming error as 1.7 degrees west or high. Now, why is the steaming error westerly or high? This is because the course has a northerly component. 345 is a northwesterly quadrant course. Whenever the course has a northerly component, the steaming error is west or high. So we now have both the errors available to us. Damping error is 2.580 east. So we have it here. And the steaming error is 1.7 degrees west. So when we combine both these errors, since they are of opposite names, we will subtract the smaller one from the bigger one. So 2.58 minus 1.0 gives the error as 0.880 degrees. The naming is given of the higher value, higher magnitude, which in this case is east. So the total resultant gyro error is 0.880 degrees east. Now, since the error is 0.880 degrees east, the spin axis will be pointing 0.880 degrees east of north. Thus, the direction of the axis will be 0.880 degrees true. Now, what they have asked in this question is not the gyro error. They have asked us what will be the direction of the axis. To make it little more tricky, they have asked the direction of the spin axis. So whenever the error is east, the spin axis will be pointing east of north, that is 0.880 degrees true.
Sir, can you please show the previous slide, sir?
Okay, beta. Okay. Any doubts in this one, beta?
Yes, sir. I did not understand how it is only 0.880 and we are not getting this course. The direction of spin axis, I mean.
Okay, all right. Give me a minute. I'll show it to you, beta. This is the previous slide, beta.
Okay, sir.
Okay, great. Now give me a minute. I'll take you to the whiteboard. Okay, beta. All right. So you see the error which we have got is 0.880 east. Now what is the meaning of this error? Let me show you. Let us say this is true north. Okay, let's mark this as true north. If the error is 0.880 east, it simply means that the spin axis is 0.880 degrees east of true north. So the spin axis is in this direction. And this is what we call as the gyro north. You can call it as gyro north also. And this is basically the spin axis. This is the spin axis, beta. Now, since it is 0.880 east of north, the direction of the spin axis will be 0.880 true. अब आपको मैं एक और एग्जांपल देता हूं जिससे ये पूरा क्लियर हो जाएगा. अगर इसी क्वेश्चन में बेटा हमारी जो एरर है वो 1 डिग्री वेस्ट आई होती, that would mean that the spin axis is 1 degree west of true north. Okay, so if we had got an answer of 1 degree west, then the spin axis would be here. This is where the spin axis would be pointing, and in this case the direction of the axis would be 359 true. So are you able to visualize and understand now?
Yes, sir. I understood this. But in the question, they are saying that we are making good a course of 345. So it should be
right, beta.
345 plus 0.880, right?
No, beta. No. They are not asking you about the gyro course to steer. The vessel is making a course of 349. It simply means that the vessel is moving somewhere like this. Irrespective of on what course the ship is moving, the gyro north is going to remain at this location only.
Okay.
Gyro will give you your course as this one. This will be your gyro course. Basically, it will be 0.88 degrees lesser than your true course.
understood, sir. Now I got it.
Okay, clear?
Clear.
Very good, beta. Great. So closing this down now. Okay, all right. So we have completed this numerical. Okay, so beta, before we proceed ahead, want to take a break?
Yes, sir. Yes, sir.
Okay, beta. So let's take a 5 minutes break, then we'll continue. Be back after 5 minutes. चलो बेटा आगे चलें. Next question. Let's go. Okay, let's move to the next one. Moving on to the next question. A ship with gyro compass uncorrected for damping and steaming errors steers 200 degrees true and gyro from position A in latitude 60 degrees south to position B in latitude 64 degrees south. Determine the speed of the ship and the course to steer from position B to A with gyro compass uncorrected. It is given in the question the ratio of PC to PD, control precession to damping precession, is 40:1. So have a good look at the question, beta. Let me know if any doubts come in. Okay, let's see the solution. In other words, they have provided us with the value of K, which is equal to 1/40 in this case. Now, this question is little different from the ones which we have done till now. Till now, we were given the ship's particulars and we were required to calculate the compass error. But now they want us to find the speed of the ship. So let's see how we go about the solution. Now, as we did in the last question, in this question also, the gyro compass is uncorrected for damping and steaming errors, but it is steering 200 degrees true and gyro. So if 200 degrees true as well as gyro course is being steered, that means the gyro error is nil, zero gyro error. Now, how is that possible for a compass which is uncorrected for these two errors? So that's only possible if both these errors are exactly equal and opposite to each other, thus cancelling out and making the gyro error as 0. So the gyro compass is uncorrected for both the errors, but is steering the same gyro and true course. This is only possible if the CLSE, steaming error, and damping errors are exactly equal and opposite. Now we have the information to calculate the damping error. So let's calculate the damping error first using a mean latitude of 62 degrees south. Now you see the ship is moving from 60 degrees south to 64 degrees south. Whenever the ship is moving, the latitude will be changing continuously, and the damping error will also be changing continuously. So whenever we are calculating the damping error for a particular stretch, we use the mean latitude to get the damping error. So 60 degrees south to 64 degrees south, the mean latitude comes out to 62 degrees south. So using this in the damping error formula, sine of damping error is equal to K tan latitude. K is equal to 1/40. It is given in the question. Tangent of latitude, which is 62 degrees, gives us the damping error as 2.695 degrees. Now, since the vessel is in the southern hemisphere, the latitude is south, the error will always be west or high. The damping error is always west or high in the southern hemisphere.
सर मीन लैटिट्यूड का क्यों दिया एक बार सर बता देंगे?
Okay, beta. Now, beta, you see, we are moving from 60 degree to 64 degree latitude. When you calculate the damping error, you can input only one latitude here, right? The latitude will be changing 60, 60, 01, 60, 02, 61, 62, 63, 64. So a doubt arises which latitude should be used here. So in all these cases, when you are moving from position A to B, we take the mean latitude to calculate the damping error. For initial 50% of the passage, the damping error will be slightly on one side of 2.695, either slightly lower or slightly higher. And for the later part, the later 50% of the voyage, it will err on the other side. So the error will be fluctuating around this figure. Somewhere it will be slightly lesser than this, somewhere it will be slightly greater than this. So that is why we use the mean latitude.
So this is like a mean damping error, sir, right?
That's correct, beta. It is like a mean damping error. Somewhere the damping error, actual damping error will be slightly higher than this, and at some places it will be slightly lower than this. Okay,
sir,
beta.
One more doubt.
Go ahead.
So,
Go ahead.
Even if you have taken for 60 degree or 64 degree, means not taking the mean, the damping error and the steaming error will be, CLSC will be, in that case also opposite also. Same, it will cancel out. Na, sir, for 60 degree also and 64 degree also.
Yeah, that's correct. But the answer will be slightly wrong.
Means if we had taken at 60 degree or suppose 64 degree also, then also we can get the speed, na, sir?
बेटा स्पीड तो आप अगर 50 डिग्री भी ले लोगे तो भी निकल जाएगी, पर वो गलत होगी ना.
अच्छा सर.
ओके, गलत इसलिए होगी बेटा क्योंकि अगर आप इसमें 60 डिग्री ले लेते हो. नाउ यू हैव कैलकुलेटेड द एरर फॉर 60 डिग्री. लेट अस से इट कम्स टू 2.6. ओके, नाउ whenever you are moving, your damping error will be higher than 2.6 all the time. Okay, so
Right.
2.6 will not be the right figure to take, na? In other words, in other case, if you take 64, the damping error may be 2.7, and throughout your passage, the actual damping error may be lesser than 2.7, right? So if you take the mean, yes, you will not be exactly on the mean, but you will be slightly higher and slightly lower than that. So ultimately, the total calculation is going to give you the average speed or the average error.
Understood, sir.
Okay, if you are taking 60 or 64, you are going to one extreme. If you take the mean, you are in between. You are taking the average.
So speed also will get average only, mean speed basically. Yes.
Exactly,
right,
beta. That's right.
Okay.
That is
Okay.
right.
Okay, sir.
Okay. Now we know CLSE is exactly equal and opposite to the damping error, since the total gyro error is 0 here. So the CLSE or the steaming error will be 2.695 degrees east or low. Now using this in the steaming error formula, we will get the steaming error formula is tangent of CLSE is equal to V cos course divided by 900 cos lat minus V sin course. The negative sign is because we have a westerly component of the course. The course which is being steered is 200, which is south 20 degrees west. So whenever we have a westerly component, there is a negative sign in the denominator. Now in the CLSE formula, we have all the values available in this formula other than the speed of the ship. We know the CLSE is 2.695. equal and opposite to damping error. And we know the course is 20 degrees. 200 is south 20 degrees west. So we put 20 degrees here in place of course. 900 cos latitude. Latitude is the mean latitude between 60 and 64. That comes to 62 degrees minus V sine course. Course is 20 degrees. So when we put all these values in the formula, the only unknown here is the speed of the ship, and we get the speed of the ship as 20.81 knots. Any doubts up to here, beta? Okay, great. So the first part is done. We have obtained the speed of the ship. Now we also have to find the course to steer from B to A. So let's see that also. Now moving on to the second part, we need to know what should be the course to steer if you want to go from position B to A. So for finding the course to steer from B to A, when we are going from position A to B, the vessel was steering 200 degrees true. Therefore, the true course from B to A will be its reciprocal, and that's going to be 020 degrees true. The position A and B are the same. Initially, we were going from A to B on a course of 200. When you go from B to A, you are going in the exact reciprocal direction, and the course also becomes reciprocal, which is 020 degrees true. Now, if we apply the total gyro error to 020 degrees true, we can find the gyro course to steer in this case. Now, the damping error is going to remain the same as the vessel is traveling within the same latitudes. So, whether you are moving on 200 or you are moving on 020, there is no change in the damping error. The damping error is only dependent upon latitude, and the latitudes are the same. So damping error is going to remain the same. The CLSE will change and has to be calculated. So now we are moving on to the next slide. We will be using this speed 20.81 to find out the CLSE. Clear up to here, beta? Any doubts?
Sir, can I have the previous slide? I just need to take a screenshot.
Okay, beta. All right. Now, before I go to the previous slide, beta, देखो अगर हम यहाँ पे mean latitude ना लेते, if somebody had taken 60 degrees south when you are going from A to B, now that will make things complicated, because when you are going from B to A using the same logic, now you have to take latitude 64. So the damping error also will become different. So you see, the whole question gets complicated. Right, beta?
Yes, sir. Yes, sir. Yes, sir.
Okay. All right. So let me show you the previous slide. Here it is, beta.
Yes, sir. Thank you.
Okay. So let us now calculate the CLSE. So calculating the new CLSE, in the formula tan CLSE is equal to V cos course divided by 900 cos lat plus V sin course. We have a positive sign now because the course is 020, which has a easterly component, and we have a positive sign with easterly component. Putting the values, the speed with which we calculated 20.81 into cos of course, which is 20, 900 cos of latitude, which is 62 degrees, plus V 20.81 sine of course, which is 20 degrees. So using these values, we get the CLSE as 2.606 degrees west or high. Why is the error west or high? because the course which we have now, 0 to 0 degrees true, is a northerly component course. It's in the northeast quadrant. Whenever we have a northerly component, the steaming error is always west or high. So combining both the errors now, the total gyro error will be the CLSE or steaming error, which is 2.606 degrees west, plus the damping error, which is 2.695 degrees west, giving us a gyro error of 5.301 degrees west or high. Now the true course to steer is 0 to 0 degrees true. The gyro is 5.301 degree high. So we add this value to 0 to 0. It gives us 0 to 5.301 degrees as the gyro course to steer. So we have obtained the second item also. They wanted us to find the speed of the ship and the gyro course to steer from position B to A. Both have been calculated. Clear, beta? Any doubts?
Sir, ये 25 marks का है numerical.
Beta, the simpler ones which I showed you earlier are 12.5 marks. This one is 25 marks, which has come in the past papers.
Okay, sir.
Okay, great. चलें आगे. Next one. Very good. Let's go. Steaming error of a gyro on the equator is 2 degrees. Allowing for the same speed and course, what will be the steaming error in latitude 36 degrees 52 minutes? So is the question clear, beta? Okay, let's see the solution. Now this question is a typical question. We have to use a specific formula for solving this question. Let's try to understand the solution. The steaming error or CLSE is given by the formula. Tangent of CLSE is equal to V cos course divided by 900 cos lat plus minus V sin course. Now, if you look at the denominator on the right hand side of this formula, the denominator consists of two components. The first component is 900 cos latitude and the second component is V sin course. Now the second component, the V sin course component, is much smaller as compared to the first component. As the speed of the vessel is going to be much lesser as compared to the peripheral speed of the Earth. We have cosine of a quantity in the back, cos of latitude here, and here we have sine of course. The value of cos lat as well as sine of course never exceeds more than 1. So the deciding factor which decides whether a factor will be smaller or greater is the initial value mentioned here. So in the first component we have 900, which is the peripheral speed of the Earth, and in the second component we have V, which is the speed of the ship. Now since the speed of the vessel is going to be much lesser as compared to 900 knots, the second component is much smaller. Now since this component is much smaller as compared to the first component of 900 cos lat, we can get the steaming error or CLSE to a reasonable accuracy even after neglecting the second component. Now if we neglect the second component, that is the V sin course component, The formula then reduces to tangent of CLSE is equal to V cos course divided by 900 cos latitude. So the formula has been simplified now. Now this simplified formula is going to give us a reasonable accuracy because number one, the factor V sine course was much smaller as compared to the first component, and secondly, the accuracy or the resolution up to which we require this CLSE or the steaming error is only one place after the decimal. So if required, we can use this simplified formula, the reduced formula. Now this being a typical question where there is no indication of the speed as well as the course, we will have to utilize the reduced formula. You see, there are too many unknowns in this question. The speed is not known to us. The course of the ship is also not known to us. So these multiple components, unknown components, variables, it is not possible to find using the detailed formula. So we will have to use the reduced formula. So we will be using this formula now to calculate the steaming error. So moving on to the equator now. So at the equator, tangent of CLSE is equal to V cos course divided by 900 cos latitude. So the CLSE is 2 degrees. It is given to us in the question. Factor V cos course is not known to us. We don't know what is the speed. We do not know what is the course. 900 cos latitude, the latitude is 0. So this converts to 900 tangent 2 is equal to V cos course. So we get a value of the component V cos course. Now using this component of V cos course, we can now find the steaming error in latitude 36 degree 52 minutes. So applying the reduced formula once again, tangent of CLSE is equal to V cos course divided by 900 cos of latitude, which in this case is 36 degrees 52 minutes. So V cos course, the numerator of the formula, is now replaced with the value which we found earlier, that is 900 multiplied by tangent of 2 degrees divided by 900 cos of 36 degrees 52 minutes. So using this, solving this in the calculator, we get the CLSE or the steaming error in latitude 36 degree 52 minutes as 2.499 degrees. Now this error could be east, this error could be west. Because we are not aware of what the course is, there are both the possibilities. So depending upon what the course is, the error could change. That's why you see in the answer we have only mentioned the magnitude and not the direction. So why I said that this is a typical question, because if you do not know the method beforehand, if you see this question first time in the exams, it will be very difficult to evaluate and find out that we have to use the reduced formula. But once you have done this, practice this numerical, then you are aware that in case of these kind of questions where there are too many variables, the speed as well as the course both are unknown, we can simplify the formula and use it for easy calculation. In fact, practically on board, whenever we are calculating the CLSE or steaming error manually, we can use this formula very much because it gives us the required accuracy. We only need an accuracy of one place after the decimal. So that much accuracy is very much obtained by using this reduced formula. Clear, beta? Any doubts coming in? Okay, beta. Great. Let's move ahead then. Moving on to the next question. Ship sails at 1200 hours from position 43 degrees north, 058 degrees 30 minutes west. To pick up pilot at 1700 hours in position 44 degrees north, 060 degrees west. The current has been setting 180 degrees true at 1.0 knots throughout. The ship is fitted with a Sperry gyro, which is uncorrected for damping and north-south speed error. If the damping ratio is 1/40, calculate the gyro course and the ship's speed, which needs to be maintained to reach the pilot station in time. Now this question looks slightly different from the ones which we have done till now. The questions which we have done were basically revolving around the compass errors, damping error and steaming error. But this question involves fundamentals or principles of chart work. That is, a current is involved here, course to steer, course made good is involved here. You need to reach a particular position, and it also involves the concepts of plane and parallel sail. We would need to find out the courses and distances to get to our answer. So let's see how this question is to be solved. Now the question becomes very simple to understand if we put all this information in a diagram format. The vessel sails at 1200 hours from position 43 degrees north, 58 degree 30 minute west. So if you have a look at this particular diagram, you pay your attention to position A here. This is the starting position of the ship. The starting position is 43 degrees north, 58 degrees 30 minute west. The ship is here at 1200 hours. Now next the question says is vessel needs to pick up the pilot at 1700 hours in position 44 degrees north and 060 degrees west. Now the pilot boarding point is this position here in the diagram, point C, Charlie point. Latitude 44 degree north, longitude is 060 degrees west, and we need to reach here at 1700 hours. Now if you join position A to position C, Alpha to Charlie, this will give you the course to be made good. So this is the course which the ship needs to make good to reach the pilot station in time. Now the next information is there is a current in the area and the current has been setting 180 at a rate of 1 knot. Now our voyage is for total duration of 5 hours. We are starting at 1200 hours and our ETA should be 1700 hours. So with a rate of 1 knot in 5 hours, the vessel will be drifting by a distance of 5 nautical miles. So what we do is at the starting position A, we apply the current vector. The set is 180, so we draw it in a direction, southerly direction, 180 direction. And the magnitude of the vector, which is equal to the drift of the current, is 5 nautical miles. So you can see 3 arrows put here. That is the symbol for current. And the magnitude is also mentioned here as 5 nautical miles. This is the set and drift of the current, 180 into 5 miles. Now if you move from position A in the direction of the current, after 5 nautical miles, the position where you will arrive is this position Bravo. You can easily find out the latitude and longitude of this position. There is no change in the longitude as you are moving on a southerly track. There is no D long. So the longitude remains same, 058 degrees 30 minute west, which is the same as the longitude of A. And the change in latitude is 5 minutes. 1 nautical mile is equal to 1 minute of latitude. So our initial latitude was 43 degrees north. If you go 5 miles down south, the latitude would be 42 degrees 55 minutes north. So we have basically obtained the latitude and longitude of position Bravo. Now if we join Bravo with chart B to C, this gives us the course to steer. You see, it's a very simple chart work current CTS CMG triangle. The resultant of the current vector and the CTS vector is the course made good. So you can see in this diagram the resultant of current, which is represented by AB, and the CTS, which is represented by BC, is the course made good vector represented by AC, alpha 2 Charlie. Now once we have put all this information in the diagram format, we should be able to calculate and find out what is the CTS, what is the total distance between B to C. We should also be able to find out what is the course made good or course required to be made good, and the total distance to be made good, that is alpha 2 Charlie. So we will be using plane and parallel sailing formula now to calculate all these items. All these items will be required when we find out the gyro error in the end. So moving further, first of all, let us calculate the course to be made good, CMG, represented by alpha 2 Charlie vector, alpha 2 Charlie, and also what is the speed to be made good. So our starting position is A, which is 43 degrees north, 058 degree 30 minute west, and the destination is position C, Charlie, which is 44 degrees north and 060 degrees west. So if you see the D-lat between these two positions, 43 degree north and 44 degrees north, is equal to 60 minutes. So D-lat is equal to 60 minutes, and the D-long is equal to 90 minutes west. We are starting from 58:30 west going up to 60 west. So the total D-long between these two positions is 90 minutes west. Now we have the D-lat, we have the D-long. We can calculate the departure. Departure is equal to D-long into cos of mean lat. D-long is 90 minutes. Mean lat between position A and position C will be 43 degrees 30 minutes or 43.5. So 90 into cos of 43.5, that gives us the departure of 65.3 minutes. Now using the tangent course formula from plane and parallel sailing, tangent course is equal to departure upon D-lat. So that gives us 65.3 upon 60, which gives us the course to be made good as 47 degrees 25.3 minutes. The course obtained by plane and parallel sailing is the quadrantal course, and we know that the vessel is moving in a northwesterly direction. So this is north 47 25.3 minutes west. This is the course to be made good. Clear up to here, beta?
Can you show the previous slide for this question?
Okay, beta, let me first complete. I will show you all the slides later on.
Okay, sir.
Now moving further, we also know the formula for distance is equal to D-lat upon cos course. The D-lat is 60 minutes and the course which we just now calculated is 4725.3. So using these values, you get the distance to be made good as 88.68 miles. Now once you obtain this distance AC, alpha to Charlie, This is the distance to be made good. This distance is to be covered in 5 hours. We are starting at 1200 hours and our ETA is 1700 hours. So we have 5 hours to cover this distance. So we can easily calculate the speed made good required. The speed to make good will be the total distance upon time. So 88.68 upon 5 hours, that gives us a speed to make good 17.74 knots. So this is the speed which the ship needs to make good to reach the destination in time. So we have calculated the distance, we have calculated the speed, we have calculated the course. We will be using all these values later on in calculation of the gyro error. Any doubts up to here? Great. Moving ahead. So now moving further in the second step, we now find out the CTS vector, that is Bravo to Charlie. Up till now we have found out the AC vector, Alpha to Charlie vector, which was the CMG vector. Now we are going to find out the Bravo to Charlie vector, which is the CTS vector, course to steer vector. Now once we find out the CTS, we find out the distance to be steamed, we can easily calculate the engine speed required by us. So for calculating BC, the starting position is 4255 north, longitude is 5830 west, and the destination remains same as C, 44 north and 60 degrees west. So if you see the DLAT now between these initial and final positions is 65 minutes north, the D long remains same as 90 minutes west. So calculating the departure first, equal to D long into cos of MLAT. D long is 90. MLAT, in this case the MLAT is going to be the mean latitude between 42 degrees 55 minutes and 44 degrees. Now if you round it off to the decimal of a degree, this also comes to be 43.5 degrees. So using this formula, we get the departure as 65.3 minutes. Again applying the tan course formula, which is departure upon DLAT, 65.3 upon 65 gives us the course to steer as north 45 degrees 7.9 minutes west. Converting it into 3-figure notation comes to be 314.9 degrees true. So this is the true course to steer to reach our destination. Now what is asked in the question is the gyro course to steer. So to find the gyro course to steer, we would need the gyro error. Once we have the gyro error known to us, we can apply it to the CTS to find out the gyro course to steer. But before that, let us find out the distance also, distance between B to C. Any doubts up to here, beta? Great. Moving ahead. Distance is obtained by the formula DLAT upon cos course. The DLAT is 65 minutes. Cos of course, the course which we just now calculated, 45 degrees 7.9 minutes, gives us the total distance to steam as 92.14 miles. Now this distance is to be covered in 5 hours by using the ship's engines, and this allows us to find out the engine speed required. Total distance to be covered 92.14 miles, time available 5 hours, so the speed would be 18.43 knots. Now this is the engine speed which is required to be maintained. So this was one of the items which was required find the ship's speed. This will be the answer for the ship's speed, 18.43 knots. Moving ahead now. Now to find the gyro course to steer, we need to calculate the gyro error. So this is where the gyro error comes into the picture now. Till now what we have done is only chart work and plain sailing. So now we will enter into the gyro error. So let us first calculate the damping error. Sine of damping error is equal to K tan lat. K is given as 1/40. It is given to us in the question. And tangent of latitude. Now the latitude in this case is used as the mean latitude between A and C. So A's latitude was 43, C's latitude was 44. The mean would be 43.5. So we have used the mean latitude to calculate the damping error, and it comes out to be 1.359 degrees east or low. So damping error is calculated. Why have we used the mean latitude between A and C? This is because the actual track of the vessel on which it will be physically moving is from A to C. We have shown point B in the diagram just to show the current vector and the CTS vector, but actually the vessel will be starting from position A and it will be moving on the CMG track, that is alpha to Charlie. So that's why the damping error will also be applicable between 43 and 44. Now moving on to calculation of the steaming error. Now when we are calculating the steaming error, we require the ship's speed, the ship's course. So course, latitude and speed are the three inputs required for calculating the steaming error. Now a doubt which arises in our mind is, we have two courses available to us. One course is the CMG, course made good, and the other course is the CTS, course to steer. Which out of these two should we be using? Now please understand that the course and speed which is used in calculating the steaming error are always the course made good and the speed made good. We do not use, I repeat, we do not use the CTS and the engine speed. CTS and engine speed is never used for calculating the steaming error. Steaming error is always calculated using course made good and speed made good. Now why is it so? This is so because the CLSE or steaming error depends upon the movement of vessel over the ground and not through the water. This movement of ship over the ground is given by CMG and SMG. So course made good is also known as course over ground. Speed made good is also known as speed over ground. So this is what we require to calculate the CLSE or steaming error. We are not interested in what the vessel is steering, what is the engine speed. What we are interested in, what is the course made good by the ship and what is the speed made good by the ship. So once this is understood, applying the CLSE formula, tan CLSE is equal to V cos course divided by 900 cos lat minus V sin course. Putting the values here, you see we have used the speed made good, 17.74 knots. And we have used the course made good, that is the course between alpha to Charlie, not the course between Bravo to Charlie. We have used the course made good. Divided by 900 cos latitude, the mean lat between A and C, alpha and Charlie, which is 43.5 degrees. minus V sine course. V is 17.74, that is the speed made good, and course is 4725.3, it is the course made good. So using these values in the calculator, we get the CLSE as 1.075 degrees west or high. So we have the damping error available to us. We have the steaming error also available to us. Now we can combine both these and get the total gyro error. Any doubts up to here, beta? Great, let's move ahead. So damping error 1.359 east, steaming error 1.075 degrees west. Both are of opposite name. So bigger minus smaller gives us the compass error as 0.284 degrees east or low. The name is taken up from the name of the bigger value, which is easterly. So this is the gyro error, 0.284 degrees east or low. Now we apply this gyro error to the CTS, course to steer. Once you have calculated the gyro error, for calculating the gyro error, we used the course made good. But once this gyro error is obtained, this gyro error has to be applied on the CTS. Now the course between Bravo to Charlie was obtained as the true course to steer. This is the course on which the gyro error is to be applied. So true course to steer was 314.9 degrees true. We apply the easterly or low error. Error east, compass least. So this should be subtracted and it gives us the gyro course to steer as 314.616. So this is the gyro course to steer. So you see this was the second item which was required. What should be the gyro course to steer and what should be the engine speed which should be maintained to reach the pilot station? And this is our answer. The gyro course to steer is 314.616 degrees gyro. Any doubts now, beta, in this question? Very good, beta. Great. So you wanted the slide, beta. This was the first slide, beta. You wanted the second one?
Sir, second last, the damping error was.
Okay.
Second last.
ओके ठीक है बेटा, मैं सारी दिखा देता हूँ, जो आपको चाहिए आप वहां पे मुझे रोक देना. This is the calculation of speed made good.
Focus.
This is calculation of CTS. This is engine speed. This is the damping error. This is CLSE. And the final one. Okay, beta. Great. Very good. So with this, we complete the presentation, beta. I'm closing down the presentation now. Okay. So how did the numericals go, beta? Easy. Can you solve them now?
सर लास्ट वाला बहुत लेंदी था सर.
हाँ बेटा, but ये पेपर में आया हुआ है, so it keeps getting repeated in the exam. ओके, आपने तो अब कर लिया है, सोचो जिसने नहीं किया होगा वो कैसे करेगा. ओके,
सर आई थिंक
So-
40 मिनट्स तो लगेगा ये क्वेश्चन को सॉल्व करने में.
या थोड़ा देखने में लेंदी लग रहा है बेटा, बट वंस यू प्रैक्टिस ना तो फिर ज्यादा टाइम नहीं लगेगा. एक बार प्लेन पैरेलल शेडिंग फार्मूलाज आपको क्लियर हो जाएं तो वो स्लाइड में देखने में बहुत ज्यादा लग रहा है, बट वंस यू अंडरस्टैंड द कॉन्सेप्ट एंड डू इट तो ये इजीली सॉल्व हो जाएगा. बाकी अगर 40 मिनट्स लग भी जाएं, दे आर वर्थ इट, बिकॉज इफ यू गेट दिस राइट देन बाकी नंबर तो आ ही जाएंगे बेटा. ओके,
Sir, sometimes they ask question related to performance test, percentage of
बेटा.
time
राइट,
settling point.
ठीक है, वो परफॉर्मेंस टेस्ट का एक क्वेश्चन पूछा गया है, वो भी मैं आपको करा देता हूँ. सो कर लें उसको भी बेटा.
सर कल करें सर, आज ओवरफ्लो हो गया सर.
ओके ओके, ऑल राइट, ठीक है, आज नहीं करते हैं बेटा. अच्छा बेटा, देयर इज वन चेंज इन द शेड्यूल. टुमारो आई एम नॉट अवेलेबल. ओके, सो टुमारो आवर क्लास विल नॉट बी देयर एंड आई विल सी यू डे आफ्टर टुमारो. ओके, सो डे आफ्टर टुमारो जो हमारा लेक्चर होगा उसमें ये जो परफॉर्मेंस स्टैंडर्ड वाला क्वेश्चन है विच कम समटाइम्स, ये इसको कवर कर लेंगे. And after this, we will be moving on to the rate of turn indicator and turn planning. Okay, इस पे भी numerical आता है हमारे पेपर में. So that will be the topic which we'll be picking up day after tomorrow. So today is 23rd, 24th PM class will be off. NAVAIDS class will be off. 25th NAVAIDS class we will pick up the remaining gyro question and the rate of turn indicator, turn planning, numerical. Right, beta? Okay.
sir.
Now one more thing before we break off. Gyro पे बेटा कभी कभी rarely rational horizon diagram पे based question आ जाता है. Okay. So मैं आपको एक वीडियो शेयर करूंगा which will guide you how to solve those rational horizon type of questions. So you can watch it tomorrow. Okay. कल इस वीडियो को आप देखना and you should be able to do the rational horizon numericals after that. It is based on the same concept as we had the rational horizon numericals in phase 1. Cosine formula, Napier rule जैसे लगाते थे उसी format में है. So watch the video and get familiarized with that question also. Right, beta?
Okay sir.
So let's start off with the echo sounder. So let me put up the presentation, beta.